Okay, so this is part 3. Let's talk about query release. Okay, so we're coming back to differential privacy. We're given a data, of course, a data set, but also a set of functions whose values we want to release approximately, whose values on the secret data set we want to release approximately. Okay, and for today, we're going to talk about linear queries. So these are ones where each function fi of the data set looks like the average of some little function, which we'll call phi I, that gets applied to each of the records. So it's the average of phi I over the records in the data set, where phi I is some map that takes, associates to each possible data record a number between 0 and 1. And what we said is that last time with the projection mechanism and the factorization mechanism, it was sort of convenient to take this view of the data set as a histogram and the set of queries we want to evaluate as a matrix. So remember what we said is we've got a histogram representation. So h of x is a vector such that in position u, it is equal to the number of entries of x that are u over n. So it is, some kind of histogram. And what we want to release is a vector of approximate answers to the queries given by this matrix F. Okay, so we said what we can do is encode the various values that phi can take as the entries of F, and then apply that to the histogram. Okay, and one running example we'll return to, we've used a lot in the class so far, and we'll return to several times today, are thresholds. So just to remind you how that looks. So there, my universe is 1 to m, and my queries are numbered also 1 to m, and phi I. The ith query is given by a small function that is 1 if x is less than or equal to I, and 0 if it's greater than otherwise. Okay. So in this case, the matrix representation looks like 1 0 0 0 0 0 0, and then 2 1s and all zeros, and then 3 1s and the rest is zeros, and then 4 1s and so forth. And then in the last row, we have all 1s except for the very last thing, which is a 0. Okay, so the diagonal of this matrix is, or everything below the diagonal is a 1, everything on the above the diagonal is a 0. Okay, so that's what F for thresholds look like. All right. So what we want to do is we want to approximate this, quantity F times H. And the first idea is that we're going to see today is that instead of sort of trying to directly produce answers to the queries by adding noise, what we're going to do is release instead a distribution on data records. Okay, so we'll think of the universe as being a discrete set of possible records, and we want to release a distribution on that set such that P has approximately the right statistics, that sort of the expectation of a function on a random sample from P hat is approximately the same as it would be for a random record drawn from the data set. So we're going to try and construct a distribution that sort of imitates the data set, at least with respect to the queries we care about. Okay, so we want to actually, and our linear algebraic notation actually makes that pretty easy to express. So what we want is that we want to find a distribution p hat such that when I multiply by this matrix, so this p hat is a vector of length m whose entries are between 0 and 1, and they add up to 1. And what we want is that it should be super close to, or as close as we can pull off to the same matrix, what we'd get by applying that matrix to the histogram. Okay. And the notion of closeness we want is in the L infinity norm. So what we want is that each of the entries, like the answers to each of the queries I would get on the distribution P, is very close to the answer I would get with a random record in in X. And in fact, and that's exactly captured by this formula. Okay, so in fact, we'll give this thing a name. We'll call this the error of p hat. Okay, and what we want is that this definition we'll be using a lot. And we want this to be small. So let's try and understand what this definition says. It says for each of the entries of these two vectors should be very similar. So what does that mean? That means that, you know, for all I from 1 to k, which is the number of queries we care about, what we want is that the expectation over something chosen according to p hat of phi I, okay, that should be very close to what we would get by choosing a random record in the data set. So that's this quantity. J equals 1 to n of phi I of xj. Okay, and it should be close in absolute value. And if we sort of just the reason that this works out, if we would just kind of like write out in terms of linear algebra what's going on, this is an inner product between phi I and p hat. And on the right-hand side, we have an inner product between phi I and the histogram for x. Okay. So far, so good. So what we're trying to do is trying to match up these inner products. The only downside is that we've got absolute values in our expression. And that's like a bummer because absolute values are a pain in the neck to deal with. And so we're going to get rid of these by looking at, by considering families. We'll only consider sets of queries that are closed under complement. Under complements, taking complements. And what that means is that if you know, phi I corresponds to a query in F, then 1 minus phi I, there's some other function which is like obtained by just sort of flipping all, if the answers are binary, we're just flipping all of the answers, otherwise we're like, you know, subtracting them from 1. That should also be in F. So what we're going to do is sort of pad out F by adding, if we need to, adding the complements of all the queries. Okay, so like, what is that? You know, that's not really doing anything particularly interesting, but what does it mean? It means that, for example, you know, for thresholds, we would add queries of the following form. queries that are like 0 if xi is less than or equal to 1, and 1, sorry, I, and 0 if x is less than or equal to I, and 1 if x is greater than I. Okay, so our matrix would get bigger. We'd now kind of have, that same, we'd now have 2 parts to it. So the same part we had before with 1s below the diagonal and 0 above it, and then a second part with like 0s below the diagonal and 1s above it. Okay, and intuitively, how does this what does this correspond to? It just says that, like, whereas, let's say this is our data distribution, okay, and the before, what we were asking was like, well, what if we were query I was asking like what fraction of the data set lies to the left of I, and now we're going to also ask, well, what fraction lies to the right? And of course, those two can be computed from each other when because they add to 1. So this isn't really changing the information content anyway at all, but it does make our lives easier because absolute values, the absolute value of y, that's the same as the maximum of like y and 1 and minus y rather. And so like that's true for any real number. And let's look at it when we look at error, how this plays out for error. So that means if I take some query phi and my data set, my estimating distribution p hat and my data set hx, what we said was like this was going to be our measure of error. Well, we can rewrite that as the maximum of this inner product and minus that, okay, which I'll put the minus sign here. And in fact, we can massage that just a little bit to look more like this kind of complement notion that we care about. So this is the maximum of phi I. And so the first term I'm not going to change, but the second term I'm going to change it. And the way I'm going to do it is I'm actually going to add the all ones vector in front. So that corresponds to like 1 minus phi I, the function given by 1 minus phi I. And I claim that doesn't actually change the formula at all, the quantity at all. And that's because when we go from minus phi to 1 minus phi, what we're doing is adding this all ones vector, and that doesn't actually change anything because this vector here, p hat minus h of x, its entries add to 0 because the entries of p hat add to 1 and the entries of h add to 1, and so the entries of p hat minus h add to 0. And so when I kind of put this all ones vector out front, it doesn't actually change the inner product because I'm adding something whose inner product with p hat minus h is 0. Okay, so this is just a little bit of kind of rewriting of the algebra so that we can simplify our expression for the error, and that's going to be really useful for us. So what it allows us to do is to say, actually, the error, if f is closed under complement, then the error of the family p hat is simply the maximum over I of this inner product phi I and p hat minus h sub x. Okay, so this looks almost the same as the thing we had before, but actually it's we've removed the absolute values by ensuring that we have the phi and its complement in the family. Okay. So this is going to be our goal. It's going to be to find a p hat that does well in this respect, such that so it's maximum over the i's goes from 1 to k of phi I times p hat minus h should be as small as possible. And what we're going to see is how we might use the multiplicative weights approach to do that.